And now I'm going to start to actually train my machine learning models. Okay, and I'm going to do this in the same way that I did for the regression example. First, I'm going to specify my model. And my model in this case, instead of regression, it's going to be a classification. I'm using the SVM library. This is a support vector machine library. But in this case, I'm using the classification model. Okay, so instead of SVR for regression, I'm using SVC. This is a support vector classification model. And just like before, the model takes in some number of parameters. In this case, for the kernel, we're not going to use the RBF kernel, which you remember from last time generates these kind of smooth contours, which work really well for an interpolation in geography. In this case, I want to just use the linear kernel, and linear will just create the best line that separates our data, because here, we have some very complex mixing, but we know that most of that just comes from error in our data set. Okay, we don't want to create this very complex division that incorporates a lot of these errors. We just want to have the algorithm give us the best line that cuts these blue and red dots apart from each other. So I'm just going to use the linear algorithm. Okay, this is up to you which one you specify. You can try a bunch of them, see which one works great. I just know in this example, linear will give us a pretty good model and will also be very fast to train. Aside from the kernel, the model will take in other parameters which dictate how much penalty it gives for mistakes. This we saw with the regression. We had the C parameter, which is that kind of error penalty. And this we want to create a variable for. We're going to run a few different models with a bunch of different C parameters and see which model produces the best results. Again, there's no rule of thumb. We never really know which C will be best, so that we want to run a bunch of different examples and then use the error measure on the validation set to pick our best model. Okay, so that's going to be a variable. And finally, our cache size. I'm just going to set it to 2 gigs. It's measured in megabytes. This is the amount of RAM that your model will take up as it's processing. The more you are able to give it, the faster the process will go. Okay, so once I specify my model, here, as I mentioned, I'm going to iterate through a bunch of different C values. So I want to set up a very simple loop. And I'm going to set CVAR, which is dictating my C parameter. And I'm just going to give it a bunch of different options starting out. So I'm going to start with a pretty small number and then work my way up from there. Okay, so it's going to test 6 different models, and it's going to vary C from 0.001 all the way to 100. I'm going to tab that over so that this model and all of my training is now within this bigger loop. So I'm going to create 6 of these different models, and I'm going to be able to pick which one fits my data the best. Once I specify the model, I want to fit it. So I'm going to call the fit function on my model. I want to fit it to the scaled training set that I generated up here. And then my features are my Y training set. Okay, this is going to fit the model using these parameters to my training data. Now I want to generate predictions on my validation set and then compare those to my known validation values to generate the error in the model. The first thing I need to do is scale my X validation set using the same scaler from before. I'm going to create a new variable called X validation scaled, and I'm going to apply that same scalar using the transform function to my X validation set. Okay, so this code is the same exact as this code. This is just to ensure that I'm scaling my validation set the same way I did my training set. Okay, now I'm going to use my model to generate predictions for this validation set based on these X features. So I have this kind of shortcut Python function to apply this prediction function for each value in my X scaled validation set. I'm going to say model.predict. This is the prediction function from my model. for I in X val scaled. Okay, so it's going to take each piece of data from this data set, it's going to apply that model, and it's going to put it into a new array for me with these square brackets. So once I have those predictions, I want to generate some kind of error value. And the error is going to be basically the number of values in my prediction that don't match or my known validation values. So first I need to compare my prediction to my validation set. So I'm going to say y val does not equal, so this exclamation point equals means not equal, to my prediction set. And right now my prediction set, because I use this Python function, it's in the form of a Python array. So I want to actually convert that first to a Python array and then apply the flatten function to make sure it's a one-dimensional array. Okay, so all this is doing is converting the prediction array to something that has the same structure as this y validation array. And here I'm testing which of those values don't match, right? And it's going to basically give me a new array which is a bunch of trues and falses. And what I really want is just a number that says how many of these are true, how many of these don't match. So I can use numpy's sum function and feed in that resulting true-false array. And it's just going to count the number of trues, okay? So here I'm creating a list of comparisons, and with the sum functions I'm counting how many of those result in trues, so how many mismatches I have. So it's going to be my error value. This is what I'm going to use to compare my 6 different models. And finally, I just want to print out a few different pieces of data so then I can figure out which model is the best. So I'm just going to print out this current C value and the current error value, casting them both to strings so I can make this concatenation. And then I'll just print out some dashes to separate out those models. So as this runs, I'll basically be able to see which error value is the smallest, and then based on that pick the right C value for my final model. I'm going to run this, fix any syntax errors here. So now it's running my model. You can see for each one it's exporting the current C value and the error value. You see here my error starts pretty high. It's getting a little bit lower. In this case, it seems like there's a bit of a limit, right? It's not getting any better. It's also not getting any worse as the C value goes up. So as you do this, you can start with a basic range. If you see something like this, where you're not sure if a higher value will result in better or worse performance, you can always just keep adding to this list and keep training other models until you see a pattern, right? So we can take these out. We know these are poor performing. We can rerun the same exact code and now just test higher values of C. So once it's finished running, you can see that it's run through our different models. Performance is really not increasing, and as you use higher and higher values of C, as you've probably noticed, the model takes a lot longer to train. So I'm just going to use this value of 1. Okay, it seems like that's a pretty good trade-off for our model.